Welcome to question 9 of paper 2 of the Higher Maths Leaving Cert 2008 exam. Part A. 20% of the items produced by a machine are defective. 4 items are chosen at random. Find the probability that none of the chosen items is defective. Okay, back in question 7, we met probabilities when looking at 4 card hands from a deck of cards. That time, we knew the total number of cards to be 52. We're not told the number of items produced here. So, is that a problem? No, because we're given a percentage, and that tells us how many parts are defective for every 100 produced. So we can look at a sample of 100 items and take it that they're representative. This problem is easy enough to do intuitively with no formulas. We're asked about 4 items. Let's build it up and start with just one item. What's the probability that it's not defective? The answer should be clear. It's 80 over 100, or 4 over 5, or 0.8. Now let's draw the second item. On its own, it'll also have the probability 0.8 of being free of defects. But what about the two events together? I mean, the probability of both having no defects. Or, put another way, what do we do with the two probabilities we got for these two events? They must be multiplied. If you multiply them, you'll get 0.64 as the probability. This makes sense, as it's obviously a lower probability to get 2 items to be defect-free in a row, but it's still a fairly high probability, better than 0.5, which is what is called even chances. So we do that to the next 2 draws as well. That is, we multiply the individual probabilities. Each time we hope to get the next item defect-free. In fact, the whole answer to getting 4 items in a row defect-free in this case is 0.8 to the power 4, which is 0.4096. We move on to part B. Anne and Brendan play a game in which they take turns throwing a die. The first person to throw a 6 wins. Anne has the first throw. Find the probability that Anne wins on her second throw. Once again, I'm going to explain this problem through, only using formulas at the very end. Let's start with a case simpler than the one in the problem, and once again build it up. What's the probability that Anne will win with just one go at the die? It should be clear that the probability of getting a 6 is 1 over 6, which is 0.1667. But in fact, the question asks about Anne winning on the second throw. So we need the probability that Anne doesn't roll a 6 on her first throw, and that's 1 minus 1 over 6, which equals 5 over 6. Next, Brendan is throwing, and Anne is hoping he doesn't get a 6. So again, we're interested in the roll not being a 6. Probability of that is 5 over 6 again. So we have 2 probabilities worked out now, as Anne gets ready for her second throw. What do we do with them? As in part A, we multiply them. So we get 5 over 6 times 5 over 6, which is 5 over 6 squared. So now it's Anne's second throw. She really wants a 6 this time, and that probability is 1 over 6. And we must multiply that by the probabilities already calculated. So that's 5 over 6 times 5 over 6 times 1 over 6, which equals 25 over 216, which is 0.116. This is the answer. As you can see, it's not much lower than the probability of 0.1667 of getting 6 on our first throw. This seems to make sense. Anne and Brendan, once again, playing this game at getting a 6. Now Anne has the first throw. Find the probability that Anne wins on her first, second, or third throw. Okay, the way this question is phrased means that we must calculate the probabilities differently. What the question means is, what's the probability that Anne wins on either of her first 3 throws of the die? In other words, she is allowed 3 opportunities to score a 6. These 3 opportunities will have separate probabilities. What do we do with them? The answer has to be that we add them, because either of the 3 rolls will do. So we're expecting a fairly high probability. Let's go ahead and calculate. We've already done the probabilities for winning on the first and second rolls, which were 0.167 and 0.116. Using the same logic, we should be able to understand that Anne's chances of winning on the third roll is, we see there 5 over 6 multiplied by itself 4 times, and then multiplied by 1 over 6. Which equals as shown, and we get 0.08. So, as we said, we now add these 3 probabilities to get, and we add the 3 probabilities, 0.167 plus 0.116 plus 0.08, and we get 0.363, which is our answer for this section. Anne and Brendan play a game. Okay, once again it's the same game. This is section 3 of part B. Now we have to find the sum to infinity of a geometric series, and in that way find the probability that Anne wins the game. In section 2 we faced the following calculation, which was 5 over 6 multiplied by itself 4 times 1 over 6. We should know about geometric series from paper 1 and know that this expression looks a lot like one. There is a small difference in that the geometric series extends leftwise instead of the usual rightwards direction. That's why the 1 over 6 is at the end this time. Well, this doesn't matter in terms of the mathematics. We should know that the sum to n terms of such a series is off by heart. Here it is anyway. So we get this expression, which is a basic identity which should be known by heart. So in this case we have to work out what r and what a is. It should be clear that r is 5 over 6 and a is 1 over 6. If we're lucky, we'll also remember that when r is less than 1, the sum to infinity also has a nice neat formula, which is, as shown, once again, a over 1 over minus r. So substituting our values in this case for a and r, we get 1 over 6 over 1 over 6, which is 1 over 36, which is 0.00277. And in fact, that is the answer. Those are the chances of Anne winning. In order to test the hypothesis that a particular coin is unbiased, the coin is tossed 400 times. The number of heads observed is x. Between what limits should x lie in order that the hypothesis not be rejected at the 5% significance level? An unbiased coin means that there are even chances of getting heads or tails. In other words, the probability of getting heads is the same as the probability of getting tails. There are only two sides to a coin, so that probability is 0.5. But if we flip the coin 400 times, what should the number of heads be? Clearly it's 200. But should we get exactly that? The answer is no, because the probability is a measure for an event in the future. We cannot say that exactly 200 heads will be produced each time, all the time. This is a source of disappointment for many gamblers who turn to mathematical probability to help them win. For this future event, we have to set a significance level and say that within it our supposition or our hypothesis cannot be called a lie. In this question we're told it's 5%. This means the total number of heads can vary within 5% of 200, and we can't call it a trick coin, which means that it can vary 2.5% on either side of 200. So we take 2.5% of 200, which is 5. So the answer, which we have worked out using reasoning, is that x must be greater than or equal to 195 and less than or equal to 205, which means that if the number of heads is actually 205, then the number of tails is naturally 400 minus 205, which is 195. Then you would be justified, especially if you are predicting tails all the time, that for those 400 flips you said, but heads came out more often than tails. You could suspect that it was a coin loaded in favour of heads, but a fair coin could in fact swing the other way during the next 400 throws. This 195 to 205 variation is not significant enough at the 5% level to reject the coin as badly made or as being a trick one, which is what the question is asking.